Hello everyone. Today we will be presenting our data mining project where we developed a dual approach to predict and profile high-risk diabetic patients. Our goal was to create a framework that not only predicts who is at risk for readmission but also helps us understand why, which enables more targeted and effective care as well.
So, why this topic? Hospital readmissions are a major burden on the healthcare system, leading to high costs and poor patient outcomes. This is especially true for patients with chronic conditions. Our initial analysis showed that diabetic patients have a 30-day readmission rate of 15.3%, nearly double the rate for other patients. This highlights a clear need for better risk management, which our project tackles head-on with machine learning. So, our goals of the project were threefold. First was predictive modeling to accurately classify patients at high risk of early readmission. Second was patient profiling to use unsupervised clustering to identify distinct patient subgroups. And finally, to generate actionable insights to provide a data-driven framework that can help hospitals reduce these preventable readmissions.
To achieve our objectives, we followed a structured data mining workflow. We began with intensive data preprocessing and feature engineering to create a clean, high-quality dataset. Our exploratory data analysis then helps us visualize key trends. From there, we pursued our dual approach. First, unsupervised learning to profile the patients, and then applying a suite of supervised learning models to predict the risk, and culminating in advanced ensemble modeling for superior accuracy as well.
So the first step was data preprocessing. Our technical preprocessing involves several key actions to clean the raw data. First, we standardized missing values, replacing markers like question marks with proper null values. We then dropped over 40% of missing data, such as weight and medical specialty. To focus purely on readmission risk, we filtered out records for patients who had expired. And to prevent data leakage in our models, we duplicated the data based on the patient number, keeping only the first hospital encounter for each of the nearly 70,000 unique patients. This resulted in a clean, robust dataset for analysis. To improve our model's predictive power, our feature engineering work was crucial. Key was managing the high cardinality diagnosis codes. Instead of treating thousands of unique ICD-9 codes separately, we grouped them into 9 major clinical categories like circulatory, respiratory, and so on. This reduced the dimensionality while preserving clinical meaning. We also created new features like prior utilization, which aggregates the patient's recent healthcare visits and encoded lab results into meaningful ordinal categories like normal and high.
Now, our exploratory analysis immediately revealed an important challenge for later on, a significant class imbalance. As you can see, our target class patients readmitted under 30 days was heavily underrepresented. This finding was crucial as it directly informed our later modeling strategy, where we needed to use a technique like random upsampling or SMOT to balance the dataset. Digging deeper into the demographics, we also found some revealing trends. The plot on the right shows a clear and strong positive correlation between the patient's age and their readmission risk. We also confirmed that clinical variables like time in hospital were highly important predictive features which helped guide our model development further on.
Now moving on to patient profiling using unsupervised learning, we use the k-means clustering algorithm. Before clustering, we applied standard scalar to normalize our 9 selected features, and to determine the optimal number of clusters, we used the elbow method, which pointed to a value of 4. Finally, as you can see on the right, we used principal component analysis to visualize these 4 clusters, which confirmed that the algorithm had successfully identified distinct underlying patient groups. Now these radar plots offer a visual comparison of the patient profiles that we identified. Each axis represents a key clinical feature. You can see the distinct shape of each profile, which helps in understanding the unique characteristics and associated risks. This visual approach makes the differences between the groups immediately apparent. The clustering revealed 4 clinically meaningful profiles, At highest risk are frequent flyers in profile 3 with 18.9% readmission rate, defined by high prior healthcare use. Next are the medically complex in profile 0 with long hospital stays. This segmentation is powerful because it allows hospitals to move beyond one size fits all approach and tailor follow-up care based on patient's specific risk profile.
Now, for our supervised learning pipeline, first we transform our target variable into a binary format and then perform the train test split as well. Our preprocessing pipeline then applied one-hot encoding to our 24 categorical columns and a standard scaler to all numerical columns for the data to better fit into those models. Crucially, to handle the class imbalance in our training data, we implemented SMOT, the synthetic minority oversampling technique, to create a balanced dataset. We then trained and evaluated a comprehensive suite of 8 different classifiers, including random forest, KNN, gradient boost, and other models as well. For optimization, we then used a 5-fold cross-validated grid search CD, systematically tuning the hyperparameters for each models, ensuring we found the best configuration while preventing underfitting, overfitting, and any other problems. Now, as we can see, the ROC curve for random forest model, which was one of the best models, shows an area under the curve of 0.99, which is very good. A curve that arcs the top left corner like this indicates strong performance, and this visual proof confirms the model's powerful ability to distinguish between high risk and low risk patients. Now, one of the most powerful outcomes of our analysis was identifying the key drivers of readmission. The feature importance chart provides now one of our most telling insights. By a significant margin, the top predictor is time in hospital, and most of the tree-based models also agreed on all of this, and number of procedures. The key takeaway is profound, that the patient recent healthcare history is a much stronger predictor of future readmission than their demographics. Now, moving on, to achieve peak performance, we advanced to ensemble learning. We created 2 supermodels by combining our top 3 individual performers, random forest, KNN, and light GBM. First was a voting classifier, which used soft voting to average out the probability scores, and the second was a more sophisticated stacking classifier, which uses a second level meta learner, in our case a logistic regression model, whose sole job is to learn the optimal way to combine the base model predictions, creating an even accurate final results. And here are the results. The ROC curves for our ensemble models are nearly perfect. The stacking ensemble, our winning model, achieved an outstanding area under the curve of 0.9985. It actually shows 1 in these plots. This powerfully demonstrates that by combining the strengths of multiple diverse models, we created a final classifier with exceptional predicting power. The slide summarizes the exceptional metrics for our stacking classifier model as well. It achieved a perfectly balanced score of 98% across accuracy, precision, recall, and F1 score, and very high area under the curve. It's not just accurate, but it's equally good at correctly identifying patients who will be readmitted and not misclassifying those who won't. This level of performance is highly significant and demonstrates the power of these advanced ensemble techniques.
Talking about limitations of our project, the primary one is the age of the data. For future work, we recommend validating these models on contemporary data, incorporating social determinants of health, and ultimately using this risk framework in a clinical trial to measure the real world impact on readmission rates. In conclusion, our dual data mining project was highly successful. We built a model achieving 98% predictive accuracy. We identified 4 actionable patient profiles with risks from 6% to 19%, and we confirmed that prior healthcare utilization is the most critical predictor. Ultimately, this work provides a robust framework that can help healthcare providers improve patient outcomes. Thank you.
Thank you.